Alright, this week we're going to learn how to apply our work equation to machines. Alright, in physics the definition of a machine is any device that changes the way work is done, but it does not change the amount of work that is done. Alright, so typically what ends up happening is machines make it easier for you to get something finished. So if you think of a machine, you're probably thinking of, things in factories and stuff like that. Machines are also things like a car. Computers are machines. But there are also some very, very simple machines that are really easy for us to apply what we've already learned in physics too. So there are 6 simple machines. There is the inclined plane, which is just kind of like a ramp. A wedge, which is very similar to the inclined plane, but instead of making a right angle at the bottom, like that does there, it's an isosceles triangle that has no right angles. Alright, there's a lever, which is kind of like a seesaw, so one end goes down, the other end goes up. There's a screw, like what you would turn with a screwdriver. A pulley, which usually involves ropes, and then you pull down and the pulley pulls something up. And then also a wheel and axle. So what happens is, if you turn this wheel, it causes this axle to turn, and then the axle can make something else move. Okay, so those are the 6 simple machines. So how machines work. They're very helpful in 2 ways. Most often what a machine will do is it'll decrease the amount of force that you have to put in to getting an object moving. Alright? Because this is especially helpful with very heavy objects, say something you wouldn't be able to lift on your own. Right? Another thing that sometimes they do, but typically this isn't as useful, but they can decrease the distance that you have to move an object by increasing the force you have to apply. This usually isn't that useful because oftentimes you use machines with things that are too heavy for you to move, so if you require even more force to move it, it's not going to work. So most often they decrease the input amount of force that you have to apply. Okay? So, machine efficiency. This measures how much work a machine puts out in comparison to the work that was put in. Alright? You calculate that by taking the work out and dividing it by the work in and multiplying it by 100. So you're finding a percentage. A perfect machine has 100% efficiency, which means the work that you put into it, the machine will put back out. However, this rarely ever happens. And in fact, as far as I know, there is no man-made machine to date that actually has 100% efficiency. Usually they have more like 30-40%. If you severely if you greatly get rid of the friction involved in all the parts, then you get closer to 100%, but it's very, very difficult to do. Alright, so whatever work you put into the machine, ideally none gets lost in the machine, but some might get lost due to friction. Alright, and then you get a certain amount of work out of the machine after the machine has done its job. Alright, but remember, friction typically occurs in the machine, which will decrease the efficiency. However, for this class, aside from when I give you problems where you have to solve for efficiency, we're going to assume that our machines are frictionless and that they are perfect machines and we can get 100% efficiency out of them. That just makes the calculations easy on your part. So, again, in reality, most machines are very inefficient. Okay? If you think about it, the work from gasoline, the amount of work that burning the gasoline puts into the car, only like 30-40% of it actually comes back into moving the car. The rest of it's lost due to friction and released as heat inside the engine. Alright, so this is a typical example of what you might see on a real-life machine. If you put 20 newtons of work in, maybe if you're lucky you'll get 12 newtons of work out. Alright, so an example of an efficiency calculation. A screw requires a person to apply 20 newtons of force to turn the screw a distance of 0.5 meters. The work output of the screw is 7 joules. What is the efficiency of the screw? Alright, so what we know here is we have a force equal to 20 newtons. And we have a distance equal to 0.5 newtons. Alright, and then we also have a work out of 7 joules. Alright, if we want to calculate efficiency, so our equation for efficiency was the work out divided by the work in. So we have work out, but the problem didn't give us work in directly. But we have a force and a distance, so if you remember, our equation for work is work equals force times distance. That tells you that our work is going to be equal to 20 times 0.5, or 10 joules. Okay? So if we want to solve for that, don't forget I do have to multiply this by 100 to turn it into a percentage at the end. If we want to solve for that, we're going to put in 7 over 10 times 100, which 7/10 is 0.7, and if you multiply that by 100, you get 70%. Okay? So efficiency calculations are really just finding a percentage. Your bottom number will always be the work that you put in. So this machine equation, this comes in handy, and this is the equation we'll be using when we assume that our machines are perfect, 100% efficiency. Alright, so get familiar with this. Because it's 100% efficiency, the work in is going to be equal to the work out. Alright? Okay? So FEDE, that's your work in. The E stands for the effort force. Right? If you think about it, you have to put forth an effort to put some work into the machine. So the FEDE, that effort part, is the thing that you do. What you do to get the machine going. Alright? Then on the right side of the equation, the FRDR, that's your work out. That's known as the resistance force, or the resistance of the machine. Alright, so FRDR is what the machine does. Alright? So, a machine doesn't change the amount of work, but what it's going to do is it's going to have a different set of force and distance that is equal to force times distance that you do. Typically what it's going to happen is you're going to have a really big FR and a little FE, but a big distance that you have to go across, and the machine will only move it a small distance. It's typically what happens with machines. So, an example of this. Inclined plane, that was our ramp. I really suggest drawing pictures of the machines when you work with these sorts of problems. Alright, and always draw yourself in there. So think about this being you. You're going to push a box along this ramp all the way up to the top. Okay? So, think about it this way. We need to know our FE we need to know all the variables for this equation, so FEDE, FRDR. And sometimes you'll see me write the little letters lowercase, means the same thing. Alright? So draw on your picture the information that you have. So you can use a 25-meter inclined plane to get a 10-kilogram box to a height of 5 meters. Alright? So we know our box is going to be 10 kilograms, but is that a force? Hopefully you are saying no. 10 kilograms is a mass. In order to convert that into a force, in order to get that to newtons, so that we can actually apply it into our equation somewhere, you need to multiply by 10. So our box is 100 newtons. Okay? And then, let's see, 5 meters and 25 meters. The problem says that you're moving the box to a height of 5 meters. That should hopefully make sense to you that that's going to be the height of your ramp, or the length of the line going up right here. So this part is 5 meters. We're going to lift that box 5 meters into the air. So the other length is how long the ramp is, 25 meters. Okay? I'm not going to tell you what this side is, because that side doesn't really mean anything to us for this sort of problem. So if you have a problem and it tells you a ramp is 25 meters long, is 30 meters long, is 10 meters long, that's referring to this part of the ramp. The angle, the hypotenuse of the triangle sort of thing. Alright? So, now we need to kind of take these numbers and figure out what they are. Okay? First off, problem tells us what is the effort force. So we don't know the force that our little person, you, are actually going to apply. So FE is a question mark. We don't know what that is yet. But our DE, our effort distance, think about it this way. If you were going to actually do this and push this box up the ramp, are you going to walk 25 meters along the ramp, or are you going to climb up this 5 meter side? Hopefully it makes sense to you to think that you're actually going to take the longer walk and walk up the ramp. So DE, the distance you actually go, is the 25 meters. Alright? So that means the other pieces of information, FR, what the ramp is actually doing is taking our box from 0 meters and moving it up to 5 meters. So since it's moving the object up, it has to counteract gravity, so that's why the force is that 100 Newton weight of the box. Alright? Many machines move things up, so a lot of times you might see problems that give you kilograms. Remember, kilograms do not go into F in any equation because that's not a force, that's a mass. Alright? If you see something that says newtons, then you can plug it in as is. But if it's kilograms, you have to convert that to a weight by multiplying by 10. And then our dr is going to be this height, the 5 meters. Okay? So now we're going to go down here and plug in what we know. So we don't know FE. So we're going to leave that one still in there. But we know DE is 25. And we know FR is going to be 100. And we know DR is going to be 5. Alright, so we're going to have 25 FE equals 500. And then we need to get our FE by itself so that we can figure out what that value is. So divide both sides by 25. And you will get FE to be 20, because 500 divided by 5, or 500 divided by 25 is 20, and then we're solving for a force, so your unit should be newtons. Alright? So that's the only problem I'm going to work you through today as far as how this works. Later in the week we will get into how all of those machines work, and where FE is and where DE is and where FR is and where DR is. Alright? Now there's one last thing that I want to reference, and that's something called mechanical advantage. This measures the helpfulness of a machine. Okay? It relates to the amount of force you put in to the amount of force that the machine puts out. The more helpful a machine is, the less force you have to apply. Because usually that's the hard thing for you to overcome, is the force. Because if it takes you more time to do it, you are able, if you have to walk a longer distance, that's not necessarily an impeding factor. But if you can't lift the object, period, that is an impeding factor. So you want to reduce the force with a machine. Okay? So the equation for mechanical advantage is your resistance force, so the force that the machine does, divided by your effort force. Okay? So in order for a machine to be helpful, you want this on the top to be a big number. You want your resistance force to be high because you want the machine to be doing all the force. And you want your effort force to be small. Okay? So machines that actually do reduce the effort force have mechanical advantages that are greater than 1, because you're going to have a big resistance force and a little effort force. Every once in a while you might see a machine that reduces the effort distance, and that's going to have a mechanical advantage of less than 1, because your effort force is going to be bigger than your resistance force. Okay? But this one is the one that happens most often, and those are the most helpful machines. Alright, so if you go back to the problem that we had already figured out that our FR from the problem, so this is the same problem we just did, was the 10 kilograms times 100, because you're lifting the box up off the ground, so that's 100 newtons. And then when we calculated it, our FE was only 20 newtons. Alright, so if you want to find mechanical advantage, you need FR over FE, which will be 100 divided by 20. Now the units on both of those are newtons. So if you notice, the units cancel out. So mechanical advantage has no units. So your mechanical advantage is just a number, and it's 5. Okay, because 100 divided by 20 would be 5. So that is it for our intro to machines. Make sure you get the assignment done. It is due by 7:20 a.m. on Tuesday. See you in class.